All right, hello everyone. So today we're going to talk about the live alt-ego using HTTP alternative services. Wait a second, that doesn't seem right. This is Black Hat, isn't it? Don't we just do evil things at Black Hat? Let me change that and correct this for 1 second. Aha, now it looks much better. So today we're going to talk about the evil alt-ego and we're going to abuse HTTP alternative services, just like the Black Hat way. So this is a joint work by me, Trishita, Professor Trachtenberg, and Professor Starobinski. All right, so take it away, Professor Trachtenberg.
Okay, so here's your mission. You have your web server, and your web server gets traffic from all kinds of different devices and over various different protocols. And what you'd like to do is move content from different protocols to different servers that handle that specific protocol. So if you have, for example, HTTP1 traffic, you want it to go to one particular server. If you have quick traffic, you'd like it to go to a different server. How do you adapt your current web server architecture to deal with this? But wait, I'm going to make things easier. I'm going to give you your choice of anyone in high tech, the stars of the field. You can pick them for your particular mission. Okay, you can pick anyone you want from Google, Microsoft, wherever companies you feel are valuable. And by the way, here are 4 people that we thought of. See if you can name them in the chat for brownie points that mean absolutely nothing, but might be interesting anyway. Okay, so can you do it? Well, luckily, HTTP has some ability to handle some of these issues. Okay, HTTP started in 1996 with HTTP 1.0 and very simple headers. So when you sent a request to a web server, you could specify a host name, a referrer, which page referred you to this particular location, your user agent, what browser you're using. And as with all software, as people started using HTTP developed additions to handle things like caching, dynamic content, request multiplexing. And what's the result? The result is that we have lots and lots of work to do. Lots of potential for abuse and security vulnerabilities, okay? In fact, HTTP is 23 years old this year. It has seen its share of all kinds of vulnerabilities over those 23 years. And in fact, what we want to show in this particular presentation is that it's still really hard to introduce secure protocol updates, even for things that look dead simple, like differentiating protocols into to different server locations.
So speaking of updates in the HTTP land, we have this new update called Alternative Services. And this is described in detail in RFC 7838, if you want to read it up. Okay, so in a nutshell, what is Alternative Services, or Alt-Svc for short? It's yet another HTTP header. Yay! Okay, what does this header do? So in short, it allows a website to specify an equivalent alternate endpoint. Now that was a mouthful. What does this even mean? So let's take a look at what this actually means. So we have the following setup where we have a client browser and we have 2 entities. Both of them are web servers. One is original.com and one is alt.com. Now let's say that the client browser wants to visit this web page, original.com, so it loads https original.com in this web browser and sends a HTTP request to original.com. Original.com, as soon as it gets the HTTP request, responds with the HTML contents of the web page and also responds with some HTTP response headers as expected. And one of the headers is this interesting Alt-Svc header. And this Alt-Svc header is pointed to alt.com at port 443. Now, what original.com is essentially trying to tell the client browser through this is that alt.com is an equivalent endpoint for original.com. So what it's saying is that the next time the client browser wants to load anything from original.com, it could choose to either go through original.com or alt.com depending on its preference. And so as soon as the client browser gets this Alt-Svc header, it immediately tries to verify whether alt.com is indeed an equivalent endpoint for original.com. So it tries to connect to alt.com over a secure channel and asks alt.com to present its certificate. And alt.com presents a certificate in the name of original.com. Now, why on earth would you ask, would alt.com present a certificate in the name of original.com? Well, this is kind of important because showing that it has a valid certificate in the name of original.com is a proof that alt.com is indeed, in fact, an equivalent endpoint for original.com. It's kind of like a security check. And the client browser needs to see this certificate in the right domain name of original.com to be convinced that alt.com is indeed a valid Alt-Svc endpoint. And once it sees this certificate that's valid, it'll cache this mapping. And by that I mean, the next time the client loads wants to load any content from original.com, it can choose either website, either web server to go to. It could either load the stuff from original.com or alt.com. And this kind of happens in the background. So even though in the URL bar you type in https original.com, in the background, your browser can choose to go to either one of the web servers, original.com and alt.com, and you wouldn't know the difference. So that's what happened. So this mapping is now cached, and in the future, either of the web servers could be used. Okay, what happens if alt.com doesn't present the right certificate? Let's say alt.com presents a certificate not in the name of original.com, but in the name of alt.com. So it presents a certificate with the domain name of alt.com. Well, then the client browser is not convinced that these two are in fact equivalent endpoints, and so it does not cache the mapping. And now what this means is that in the future, when the user wants to load stuff from original.com, it will only use original.com and not use alt.com because it doesn't trust that alt.com is actually a valid and equivalent endpoint for original.com since it did not present the correct certificate. So if the certificate is right, this mapping between original.com and alt.com is cached. If not, then it's not cached. And that is essentially how the Alt-Svc header works.
Okay, let's take a G-rated look at the anatomy of an Alt-Services header. You start with the protocol, which could be HTTP 1.1, QUIC, H2C, FTP, what have you. Then the domain to which you would like to transfer control. So the user types in a particular domain. The alternative services header says, if you're using this protocol, go to this other domain. And this port, 123 in this case. And each alternative service header has a maximum amount of time, maximum age, that this header should be valid. Ideally, it should be taken out of the cache after this number of seconds. Alternative services are used for things like load balancing. If you have a lot of different clients and you'd want to balance easily. Client segmentation, segmenting clients into different classes. And advertising endpoints with new protocols. Okay, so if you have a different protocol that does something different, rather than having one server handle all the different protocols, you can have different servers and you can actually use alternative services to handle it on the client side without needing to handle the machinery on the server side. We identified 5 vulnerabilities of alternative services. A number of them currently have CVEs. So the first one is port scanning. You can use alternative services to scan ports that are accessible from the victim machine. So even if the victim is behind a firewall, this allows you to scan other machines that are accessible only within the firewall. This also allows you to scan the victim's machine itself. Distributed denial of service, by having alternative service redirect on your browser, on your web page, you can get connecting devices to transfer access to a particular site that you're trying to target. History exfiltration, trying to identify which sites a victim has visited. Tracking trying to track a victim as they go from one ISP to another. So if they're in a cafe and then they move to another location, you can use alternative services and what has been cached to identify and fingerprint the same device. And last but not least, malware bypass, malware protection bypass, where you can bypass some of the simple malware defenses that are already set up in current browsers. We have two possible case models that we consider in our work. The first one is when an attacker controls only a website. So there's a website, the attacker controls it, and victims connect to that website. A slightly more sophisticated attacker also gets to monitor victim network traffic. And this is an attacker that, for example, could be someone who owns a router or a Wi-Fi spot in a cafe, airport, something that provides free Wi-Fi. And there, the attacker might control the remote site, but also has access to the victim's network traffic. For the purposes of this presentation, we'll look only at case one, just since we have a limited amount of time. Now, you might ask, why is this so bad? So, okay, you can cause some damage with alternative services. What does it matter? Well, one of the key things is that the alternative services header gets managed below the user's access to the browser level. What I mean by that is the victim does not actually see that they're being transferred to a different domain. And in fact, this different domain transfer is not even visible to JavaScript. So it cannot be detected using JavaScript detection mechanism. No user interaction is required to affect the alternative service transition. And it's thus also mountable by a third-party website that might be on an existing site. Okay, so this is particularly insidious. The victim, unless they're going into the internals on their operating system, if they're just using their browser like most people do, has no idea that they're actually being transferred to a different location.
All right, so now let's go over our first attack, which is port scanning CVE 2019-11728. Now, what is this attack all about? So this attack is all about distributed port scanning from the context of the browser. Now, what does that even mean? So that basically means that as an attacker, I can get whatever victims that I have that visit my website through their browsers to do the port scanning for me. Now, the setup in this attack looks like the following. So there's a victim on their browser, and there's an attacker who has a web server for evil.com. And then the attacker somehow gets the victim to visit their webpage, http:/evil.com/p1. Now, as soon as the victim visits the webpage, the attacker then sends back the HTTP response, which contains the contents of the webpage, obviously, and also an Alt-Svc header. Now, the attacker cleverly sets the Alt-Svc header to point to whatever IP address and port that the attacker wants to do the port scanning of. So in this case, the attacker wants to know if port 25 on the victim's machine is open or closed. So it sets the Alt-Svc to this interesting value of localhost port 25. Now, what does this even mean? This basically means that the attacker is telling the victim that it has on its own machine an alternative endpoint for evil.com. That's literally what it's telling it through the Alt-Svc header. Now, the victim's browser doesn't know any better, so it'll just go through the routine checkup and verify and try to verify this endpoint and see if it indeed is a valid alternative endpoint for evil.com. So it will then try to connect to localhost port 25. So it will connect to port 25 on the victim's own machine. And in doing so, it will then realize whether the port 25 is closed or open. So in this case, we have two scenarios. So scenario number one is when the port is closed, and the second scenario is when the port is open. And for your reference, the time axis moves downwards, as you can see on your right. All right, so let's go over scenario one. So if the port 25 is closed on the victim's machine, what happens when the victim's browser tries to connect to this port is that the port will immediately send a reset packet and say, hey, I don't want to talk to you. I'm done and I'm closed. So it'll just send a reset packet and that'll be the end of the communication. However, if port 25 is open, then there's going to be a few more packets that are exchanged. So for example, the TCP handshake packet and other packets may be exchanged before whatever application running on port 25 realizes that this is some sort of like weird connection that doesn't make any sense. And so port 25 is then eventually going to send a reset packet and that terminate that connection. And so in this scenario, the victim browser will clearly know whether the port is closed or not, because these are two very obviously distinguishable scenarios. So the victim's browser will definitely know whether the port is open or closed. However, the question arises here is that how on earth is evil.com sitting somewhere far, far away going to exfiltrate this information from the victim's browser? Now, the victim knows, but how does this evil.com get this information out of the victim's browser? Now for that, we have to use some clever timing side channel analysis. For this, consider the following threshold in time. So this threshold is marked by a green line on the slides. So up until this time in this process, the victim's browser, if the port is closed, the victim's browser already knows that localhost port 25 is not a valid alternative services endpoint for evil.com because it sent a reset packet without presenting a valid certificate for evil.com. So by now it knows that this is not a valid endpoint. However, if the port is open, the victim browser still hasn't received a valid certificate for evil.com, but it also hasn't received a reset packet from port 25. So it still doesn't know whether port 25 is indeed a valid endpoint for evil.com or is not a valid endpoint. So it doesn't know at this point. Now, how do we as the attacker use this information to exfiltrate the status of port 25 from the victim's browser? For that, we do something very smart. So what we do, the attacker, as soon as you hit this green threshold, the attacker does an automatic redirect through JavaScript. So you just have a small snippet of JavaScript that measures the time, and as soon as you hit this threshold, you redirect to evil.com/p2 from the original web page, which is evil.com/p1. And because now the client has loaded this new web page, the attacker gets the opportunity to present a new Alt-Svc header, and this time the attacker points the Alt-Svc header to a domain that it actually controls. So in this case, this is evil2.com at port 443. Now, what happens here is that if the old Alt-Svc that was specified to localhost port 25 was invalid and the victim's browser already knows that, so that would happen in case the port was closed, the victim's browser already knows that port 25 is an invalid Alt-Svc endpoint. It will try to connect to the new endpoint and be like, okay, well, the old one didn't work. I know that, so might as well just try my luck with the new one and see if the new Alt-Svc endpoint is valid. However, if the port was open, so if localhost 25 is open, then the victim's browser still doesn't know whether localhost 25 is valid or invalid, so it'll defer any attempt to verify whether the second Alt-Svc specified to evil2.com is valid or invalid until it can figure out whether the original Alt-Svc specified was valid or invalid. So what does this mean for us? In a nutshell, what this means is all the attacker has to do is the following. So all it has to do is look out for any connections to evil2.com. So if it gets an immediate connection to evil2.com, then it knows that port 25 on localhost on the victim's machine must have been closed, because why else would they then try to connect to the new Alt-Svc? And it would only do that if it already knows that the old Alt-Svc was in fact not working. However, if you don't get a connection to evil2.com immediately on presenting this header to the victim, then you know that localhost port 25 is open, because you know this because the victim is, you know that the victim is still in the middle of trying to verify whether that port was in fact a valid alternative endpoint for evil.com or not. So that's all you need to do. You just need to monitor whether you get an immediate connection to evil2.com or not, and you will know whether port 25 is open or closed. And so what can you do with this? So with this, you could do the following things. You could obviously do distributed port scanning. So you could just get a bunch of clients on their different browsers to do the port scanning for you. You could also scan things that you probably couldn't access directly. So localhost machines, so you could like scan the victim's local host, the victim's own machine, obviously, as we've seen. You could also scan machines behind a private network or a NAT that only the victim can access, but you as the attacker do not have direct access to. And you could also do things like scan all TCP ports. So if the victim's machine is using the Firefox browser, web browser, then you can scan TCP ports. If the victim's machine is actually using Chrome and visiting your web page through Chrome, you can actually scan UDP ports, some UDP ports through that. And the best part of all is that the attacker's identity is not revealed, because this happens because the victim is doing the scanning on behalf of the attacker. So why would the attacker's identity be revealed? So that's the best part about this attack. All right, so now time for a demo. So in this demo, as you'll see, we've set up a website which does exactly the kind of scanning that we described previously. Now this website takes two input parameters from the user, an IP address and a port. And this is the IP port pair that the website will scan through your victim browser and then report whether it's closed or open. And so we are going to be demoing this tool as a victim. So we'll be visiting this website through the victim's browser, and we'll give it our own IP address and port. And basically, we will see if the website is able to get the scanning to work in the way that we described or not. All right, so demo time. Okay. So here you see we have the website that we set up for this demo. It takes an IP and a port as HTTP parameters. So we gave it localhost and port 7000 as the IP and port. And it reports that port 7000 on localhost is closed. Now, we're on the victim machine, so we can actually just go and open port 7000 on the victim's machine. And then we can reload this web page to see if it indeed reports whether this port is open or closed. And now we see that it reports that the port is open because we just opened it. And we go to the port and we see that there's a bunch of traffic. And this is the traffic that the victim's browser sent to this port to try to verify whether it's a valid Alt-Svc for the attacker's domain.
Okay, and now for the fifth of our attacks, abuses, malware protection bypass. So let's say you're a victim browser and you want to go to www.dangerous.com. Now, dangerous.com is not actually a dangerous site. It happens to be, it seems like a perfectly reputable site. But let's assume for the sake of this presentation that it's a dangerous site, okay? So if it has been deemed a dangerous site, we have something called safe browsing, which will block dangerous.com when you've typed it into your URL bar, or in images, in HTML code, and will display the following really sinister, scary alert when you try to access dangerous.com. Deceptive site ahead, attackers may trick you into doing something dangerous, etc., 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 which we wouldn't want at Black Hat Asia. Okay, so consider now using an alternative services to do the following. Set up your own www.example.com website and include an alternative service header that redirects all traffic to www.dangerous.com. Now, as I said, alternative services function below the browser. And what happens is it also functions below what the safe browsing scanners look for. So they'll look for example.com, see that it is perfectly benign, and not recognize the fact that the clients will be shunted to dangerous.com. Okay, and in effect, we have set up a turnstile, but we have a wide open hollow path right next to it. And this allows you to bypass malware protection on these browsers.
Okay, but why is this actually dangerous? Now, to answer this, we need to examine closely how most of these website malware scanners actually work. So let's say we have a website, example.com, that has an Alt-Svc example2.com. And we have an automated scanner that wants to scan example.com for malware. So what the automated scanner does is it just loads all of the content from example.com and it examines the content of example.com and does not, in fact, examine the content of example2.com, so the Alt-Svc. So the Alt-Svc endpoint is actually not verified, and as long as the original endpoint has benign content, these automated scanners will not block the original endpoint. So this actually leads to two different scenarios. So the first scenario is kind of like the not useful scenario, where we have two websites, obviously the original endpoint and the alternative endpoint. And so the original endpoint is example.com, alternative is dangerous.com. And both of them host malware. So in this case, it's kind of like pointless because the automated scanner is going to check the original endpoint. It's going to see the malware and game over, bam, this website is blacklisted. However, the more insidious thing to do would be this. So you have the original endpoint host the benign content. So there's only benign content on the original endpoint, and all of the malware, all of the dangerous stuff is on the Alt-Svc endpoint. And this time what happens is the automated scanners look at the benign original endpoint, passes a check, and voila, nothing happens. And the original endpoint is, in fact, not blacklisted because the scanners never checked the Alt-Svc. However, we know that browsers, in fact, do honor the Alt-Svc, and so they, in fact, will load the content from the Alt-Svc, and so they'll end up getting like this whole, all of the malicious content that these scanners were trying to block in the first place. And so a lot of automated scanners, pretty much every one of them is vulnerable to to this attack because no one checks the Alt-Svc. So URL void, buyer's total, security, IP void, all of these are vulnerable to this type of two-faced content attack. So to demo this, we basically have a setup where we have an original endpoint that hosts benign content and an Alt-Svc that has malicious content. Now let's take a look at the demo. So we have our website that has benign content. So this is a benign website, original endpoint, nothing wrong, wholesome content, everything's hunky-dory. However, we see interestingly that this website specified an interesting Alt-Svc that in fact is blacklisted for having malware. But we will bypass this blacklist, as you'll see, because this is done through the Alt-Svc. So you reload it, and the reloaded content actually comes from the Alt-Svc, and it's scam content, it's malware, and it's still loaded by your browser because the safe browsing on Firefox does not check the Alt-Svc when it's looking for blacklisted content. So to prove that this is actually a blacklisted website, we will visit this website directly. So we visit the Alt-Svc directly through Firefox, and we see that this time it is in fact blocked. If we visit this website directly, it's marked as a deceptive website. Firefox does not let you visit it. However, if this is used as an Alt-Svc, then Firefox allows this website to get through.
Okay, so we've shown these horrible abuses of alternative services. How can you mitigate them? We're responsible researchers. The port scan and distributed denial of service attacks can be mitigated by blocking sensitive ports, just like you do for JavaScript, but also at the lower level of alternative services. Safe browsing exploit, malware protection bypass, can be mitigated by doing domain checks for alternative services headers and not just links that are clearly visible in the website page. The tracking and history exfiltration attacks can be mitigated by isolating the alternative services cache so they cannot be used for tracking. Okay, as I mentioned, we are responsible security researchers, so we disclosed all of these attacks to industry, to the 4 browsers that were affected: Firefox, Tor, Chrome, and Brave. And this matrix describes the current state. So Firefox and Tor both patched the port scan and distributed denial of service vulnerabilities, and we got CVEs named for them. The malware bypass protection, as far as we know, remains unpatched. It's still there. Tracking and history exfiltration is in process, but we haven't seen any concrete results yet. And so to conclude, you have this new but widely adopted alternative services header. It seems like a very simple idea, a simple additional header to a well-understood protocol, and it's vulnerable. We found 5 attacks, despite the fact that HTTP has been around for a couple decades, and the fact that the browser developers are actually very competent. You know, they have security professionals, they have a clear understanding of how to build browsers, and yet it's not easy to secure anything, much less a simple HTTP header. So our conclusion is, don't drink an alternative service. Thank you very much.